Hello, Max. How you doing?
Hello. Testing, testing, one, two, three.
Yeah, I
How's
could
the
hear
mic?
you. Yes, working good. Before we get to your talk, you get to introduce yourself and the talk to those who will be watching the Q&A video in the future.
Hello, I'm Max. I'm a professional D programmer. I work for Symmetry and the D Foundation. The genesis of this talk is effectively just giving profiling advice a lot and wanting to kind of get it in one place. So there's hopefully something there for all platforms. Although unfortunately I didn't quite get around to putting the Visual Studio profiler in it. That's the only thing that's missing. I tried to get some microarchitecture in there, but I had to kind of condense about something like 40 years worth of microarchitecture into like 3 slides. It's good enough for some intuition, but stay tuned for the our YouTube channel, the bits I couldn't fit in.
Why this talk?
It's the kind of topic where having something to throw people at is quite useful in the sense that eventually, rightly or wrongly, everyone feels the need to profile their code every now and again, and it's nice to just sort of lay down the basics of what tools are available for a given platform and how to go about using them properly. That kind of thing is mostly just from getting annoyed answering the same question too often on Discord.
Where does your profiling background come from?
I think it's the favorite. I'm not unique in saying it's a very fun kind of folly to play with, kind of trying to make code faster. The way I actually learned D partly was hopefully everyone listening to this has used Compiler Explorer. I basically learned D just by playing with the compiler on that and just looking at the output and then running the program every now and again. Obviously, when you get past the kind of basic hello world stage, when you start meta-programming, just seeing can I make this construct get down to as few instructions as possible and that kind of thing. As for the more recent kind of profiling stuff, the more you learn about microarchitecture, the more you want to measure things, and the best way to measure stuff is to use the performance counters that the CPU exposes. And basically, the only way to get a good overview of those without just crunching all the numbers yourself is with VTune. So I had to use VTune for that. It's a thumping great program, but it is very, very effective.
So the profiling was just an interest that you got into after you got into programming, but connect the dots for us here. You were a physics major, yes?
Yes.
So how does the programming fit into it?
In terms of like, obviously, I have two programs for my degree, but I'm but a mere undergraduate, so I haven't really done anything particularly interesting or useful. The programming itself was something where I had a rough interest in physics from maybe when I was 14 or 15, and then just sort of started programming as a way of not doing my coursework when I was 16. Which is a very nice distraction. So I sort of kept going with it. They've basically been separate. So I've written some basic like electromagnetism sort of simulators and things like that. Nothing super sophisticated, unfortunately. Like the ultimate goal I'd like to write at some point is a relativistic ray tracer. So you can simulate like the light around black holes and things like that. Like if you've seen Interstellar, that's what that is. But that's not a weekend project.
Right. So how did you get into D?
Well, I learned C++ because, as far as I can tell, it's from a purely kind of egotistical perspective because someone said it was complicated. It would have been just before C++ 14, I think. I just have a PDF of sort of behind this latest book. And then the D thing, I think, was basically just following Andre. I think it might have even been by accident because there was a thing where I noticed that there are a lot of people who I recognize from CPPCon videos on YouTube cropping up in the D forums, and then next minute you're actually in a call with them because it's one of the things where I didn't really know enough about programming to actually really kind of consciously choose D back then, but then I kind of went off it a bit, but then came back to it again maybe a year or two ago. No, that's less than that, maybe because I did the Symmetry Autumn of Code and then just sort of didn't code for a while and then came back. But I've been lurking on the forum for years now.
Referencing one of your slides, Max, Elijah says Pareto principle, e.g. Amdahl's law.
Well, if there's parallelism, yes, but it can just literally be that some parts of the program aren't used at all. Like on a much more practical basis, if you hear someone complaining about the speed of a given bit of a program, they're usually right. Like programmers do have good intuition, but it might be that it only runs like once on startup, and it doesn't matter. It's more basic than that.
You mentioned your SEAC project, and if I remember correctly, it was gathering statistics or was it performance of?
It was basically lots of exploratory things on build times and a little bit of runtime benchmarking, but it just didn't work. That's the issue.
So,
But
yeah,
that lives on. That lives on, and I'm going to write another benchmarking library because it's the kind of thing where I already use the library I have, but it isn't perfect. But doing benchmarking right is something that I find really important that a lot of people do wrong, which is separate to profiling, the different things.
the connection there between the SAAC project and this talk, I mean, it's all about performance. I mean, is this a more than just a passing interest for you? Is it a
Well, it's definitely more than a passing interest, but it's not. I think I'm fairly grounded in the sense that I don't spend all day fiddling around with like bit shifts and things like that. You do notice that some people can massively underestimate the ability of the compiler to optimize their code. It's definitely a fascination, but it's one of those things where it can seem very low level, but I find optimizing some things to actually be even micro optimizing things to be very high level in the sense that you're not dealing with, like, I don't find OS development interesting, for example, but trying to kind of bully your code to run the fastest possible on this given processor is quite interesting.
You say that you were tired of repeating the same stuff all the time. What are people doing wrong when it comes to performance?
Well, I don't think it's that they're not doing it wrong in the sense that they're mostly people who are new to native programming and maybe not sure exactly where to look tool wise, or for example they're using perf, the status quo for profiling on Linux, but they're struggling to kind of see the big picture of their code, so they need to switch to a different tool. For the most part, most programs are actually fairly efficient. If you look at a really horrifically slow decompile, it will usually be averaging a good enough instruction per clock that it's actually not memory bound, it's just doing way too much work. The issue that we have with modern software, as far as I'm concerned, isn't so much that JavaScript is particularly slow. It's not particularly fast. As far as I'm aware, like Node.js is roughly as fast as DMD, which is miraculous, but it could be a lot faster if we just used a proper language. But just the sheer amount of stack and work that stuff has to do to get to the things that really matter, and the amount of memory allocation, which is what actually really bites in quite a few programs.
Referencing allocation is slow in your talk, Elijah says, I want bumping, copying, NURSY.
I assume that's supposed to say nursery, but
Nursery,
basically
yeah, okay.
bump the pointer allocation for batch work. It is not a bad idea.
All right, so time out real quick. You answered him in the text. You said bumping is not a good idea at scale, IMO, and then his question is why?
In a small batch process, you can do it never free. It's actually a win. The OS cleans up after you, no one cares. In a large program, firstly, it can lead to a lot of memory fragmentation. So if the allocations are just in the wrong place. Second, unless your allocations there's a lot of temporal locality or temporality in the actual pattern of allocations, it can be quite inefficient. But it also means that the humans stop caring about the amount that they allocate. There are things in like DMD, for example, uses this bump the pointer scheme, and something like 80% of memory is never written to that it allocates in these large compilations, which isn't due to the allocation scheme, but is due to the fact that there was a kind of feeling. Here, for example, you're running just a simple kind of test program. That looks like a huge win because it never has to free anything. But then when you start working on, say, one of our large non-specific what it does programs at work, that's when we do get our compilations that use like almost all the memory my machine has, like all 64 gigs of it. It's something that you have to kind of very, very carefully measure at different scales. The thing with allocation isn't so much that the allocation should be made faster, but rather that if you're spending too much time allocating, you should be allocating less memory. Like I see people saying, oh no, you can't use GC because it's too slow, and then their alternative is calling like malloc on like in the loop versus pre-allocating. It's a call to like a good malloc implementation on the fast path where it can just dump memory back at you is still like easily enough to do maybe 100 or 200 instructions if you're in some magic world where you didn't have to rely on the memory too much.
So Elijah says not plain bumping, copying, nursery. So you GC to bring things back together, and then regarding temporal locality, promote to older generations. And he says to see the generational GC hypothesis.
Yeah, if you have a strategy and it actually matches what your program does, it's nearly always better than a naive GC that has to work for everything. This is the power of the stood experimental allocators. They do make composing these patterns much better. It should really be in stood by now, if I can be slightly political.
And Elijah says people say GC is slow, but then, or no, you say that people say GC is slow, but then use malloc in a loop. And he says, yes, malloc is slow too. And this is something I harped on in one of my GC posts. It's a common strategy in C and C++. You don't allocate in your hot loops, right? You pre-allocate, and in D with RGC, it's the same strategy, right? You pre-allocate and then go into your loops. You don't replace the GC with malloc in your loops, but it's a very simple strategy.
Really, also, you can allocate on the stack very easily in D. You just declare a variable.
Right. Yeah. But I mean, if you need to allocate an array, you put it on the stack, or you reserve, use reserve, or whatever you do. But you do it before you get to your hotspots. But while you were answering that question, I was looking your microarchitecture slides went by, and you said you have more to say about that in future talk. But in the meantime, is there any source material you would recommend for people who are not well versed?
It's not a very good book, but it has almost all the information you'll ever need. Hennessy and Patterson. I did synthesize. There are basically computer architecture books, all two of them. There's this, the baby version of this, and then there's a book called Modern Processor Design by John Paul Shen, I think. But this is written by the people who came up with RISC. It covers basically everything. I mean, the only issue is it's definitely written for engineers. There's a certain level of approximating before analyzing, if that makes sense. Whereas the other book I mentioned is much more focused at processor implementers. Although the only way to really see how a modern processor is actually working is by reading patents, really. Like it's all of the documentation, if there is any, is basically a slightly hyper-normalized version of the processor. So whereas Intel publish about maybe, I think it's 700 pages of optimization manuals, AMD publish about 40 pages, which is basically just a big list of performance counter IDs, which is better than not having them. And then Apple publish nothing. Those are the main three big hitters at the moment. Although one thing that is quite interesting is that the Fujitsu A64FX, which runs the supercomputer I can't remember the name of in Japan, Fugaku, they actually publish a really, really detailed thing on how their processor actually works, because it's designed for HPC customers who need to know. You or I can't buy one because we're not special enough.
I haven't read those books you mentioned, but I would like to add to the list. Randall Hyde has the Write Great Code series. You can get it through No Starch Press, and the first book in that series is Understanding the Machine, and he goes into quite a bit of detail about architecture and CPU design and a lot of fundamental stuff that a lot of people don't get. Among these profilers that you cover in your talk, which one do you use the most?
VTune or AMD's knockoff of VTune, which is UProf, because I'm on my work machine is an AMD 3950X, and Intel obviously aren't going to support their rivals' processors. Even they could. I know they could, because I looked at the system calls it uses.
The last time I looked at VTune was many years ago, and I believe it was commercial only at the time. Is it still commercial? Or is it free?
It's free. It's definitely not open source. As far as I'm aware, it's on a do what you want license. With obviously, it's the usual kind of like no warranty clause, because it's part of their one API thing now. So it's not just VTune. The whole point is you're supposed to download this big package of tools and libraries, so you get access to not only VTune, but also, I don't think I mentioned it in the top, also like Intel Advisor, which is not quite a profiler. It's basically a performance analyzer. So it will find loops in your program, for example, and advise you on whether you should have vectorized them or whether you should offload them to their GPU. The latter feature, as far as I'm concerned, isn't particularly useful because it only works with GPUs, who actually has an Intel discrete GPU. But it's all part of their one API data parallel C++ thing, which is nowhere near as good as dcompute.
Guillaume says both Intel Amplifier and AMD UProf work fine with D and are free. I wonder, Walter, what sort of profiling software have you used over the years?
I usually use my own profiler. DMD has a profiler built in.
Yeah, but prior to that,
basically just the system clock.
You've never used VTune or anything like that, then?
I keep looking at VTone, thinking I should figure out how to use it, but I've never bothered. I've used gprof a few times. Going back even to the 80s, the C compiler I wrote was able to instrument its own code for profiling, and I'd use that all the time. In fact, I use that a great deal, and that's made its way into the DMD compiler as well. You use the -profile switch, and it inserts code to do the profiling, and then when your program finishes, it prints a report. It's a simple and effective means of doing profile.
So, Max, I don't recall you talking about when to profile. This is something people often get wrong. What do you say on that point?
I don't really think there's, it's not the kind of thing where you can follow a flowchart, which is why in the early bits of the talk I mentioned, I think you should get a kind of regular rhythm going where you should have, if there's any core functionality that you can measure, you should have benchmarks going regularly as part of your CI, assuming it's reliable. And then you should just do a profile every few weeks or so, because it's something where you can't squeeze blood out of a rock. Some things will just have the performance that they are because of the algorithm or because of the, because whatever you're actually running on. Profile to test your assumptions and when you think it's just getting too sluggish.
With these instrumenting profilers and things like that we have in the statically compiled language world, is there more data that you would like to get from them than what they give you now?
It depends really, because I'm not a huge fan of instrumentation for performance profiling. Any metric you're interested in, it's basically a question of either someone having done the engineering for you already or having to do it yourself.
To rephrase it, are you missing anything from the profilers now?
It would be nice to have a kind of standardized API where you can, say for example, you want to get as much rough data in one run as possible. If you can use the performance profiling with a sampling profile like VTune, but also tell the compiler to emit instrumentation for, say, memory allocations, things like that would be quite useful, because memory allocations in particular, as I said in the talk, really does benefit from instrumentation. As for metrics, most of them, the ones that matter, are actually built into the CPU these days. It's fairly easy to get correlation back to the source code. If you want to get really, really sort of deep, then you can use some kind of emulated system like Valgrind or like Intel Pin. Because one of the things I was trying to do for this talk was to actually run basically just compiling Hello World with DMD through a microarchitecture simulator called Gem 5 with different memory hierarchies. But it turned out that it was taking about 4 minutes to compile Hello World, so I had to give up on that.
So, Max, what's the key point you want people to take away from this talk?
Profile more often, but do it right, just as a habit. I think that having a regular rhythm to benchmarking is almost as important in the sense that it's really hard to do in a cloud environment, but something that I want to do for ages is to just have bits of Phobos running regularly to just track how fast they run, because things do regress, unfortunately. And having historical data to spot trends is really, really helpful. I think Vladimir has something for build times.
Brian has a question now. You say profile more often, but do it right. How might programmers or companies do a first step towards always profiling correctly?
One of the nice things about modern profiles is that they can nearly all be automated quite effectively, because a lot of them have had a kind of baptism in fire in HPC. So like you can run VTune on the command line in 1,000 miles away. It can host a web server and serve the data to you remotely. With perf, if you just use -G and check that it can actually resolve the call stack properly, if you do that to start with, you're basically fine. Anything more detailed, you have to use other flags, but that will give you reliable data. The only risk is that people do complain about if you have the sample rate set that it basically aligns with something in the program and you miss things, but I've never actually noticed that to be an issue myself. As for the profilers that are commercial products, they all have basically templates for the analysis they want to kind of funnel you down into, and as long as they have call stack sampling enabled, they're fine.
Elijah asked, do you know of any good resources beyond Hennessy and Patterson on modern cache coherency algorithms?
Well, there's a book called Memory Systems by Bruce Jacobs, which is getting on a bit, but it might have the raw ingredients in it. Unfortunately, it's from 2007, but it's by far the most detailed book on memory systems. As for cache coherency, I would have thought you'd probably have to just go patent digging. It's not something I'm hugely knowledgeable about. Unless the company tells you, it's fairly rare to actually know anything about the specifics of their implementation. AMD used to publish more detail than Intel on their caches, but I think that ended with Zen. I don't think the current Zen ones have that much detail, but with the crap generation they had before Zen, like Bulldozer, they did used to publish more information. I would have thought that Hennessy and Patterson would be a good start, but it might not be. Also depends what you mean by modern.
Are you employing any of these things in your job at Symmetry?
No.
Okay.
Well, so we write a language, and that might be gaining a profiler, but we're basically changing the type system at the moment. So any and all work on the kind of lower levels of the implementation would be foolish, because we're still changing like large details about the language itself. We have a basic profiler. I just don't think it's very useful, but it's not a priority for us at the moment.
Esna asks, did you profile Phobos or DMD? And if so, did you find any parts that you think could be improved?
I end up profiling DMD quite a lot. DMD, for the most part, is actually fairly efficient. The issue is that it just does way too much work. Obviously, Stefan would disagree with me on that because he wants to find concurrency and parallelism everywhere, which might be possible. For the moment now, the issue with DMD is just having too much on its plate at the same time. The memory allocation is horrific in some places, though. Like, there are some kind of really classic OOP issues where we have things that have a type which end up inheriting from type instead of having a member of type, i.e. rather than having basically just a string of 2 pointers, i.e. a pointer for the name and a pointer for the type of some identifier, we end up with a pointer plus 300 bytes worth of members to represent the actual type of that identifier. This is the reason why I say that profile GC is very useful, because you can actually get the type of the allocations, as opposed to if you use like Valgrind massive or heap track, it just tells you where but not what. CTFE is very slow. If you profile CTFE, there are some really horrible things in there. Like, it spends, I forget what I profiled it on, but it spends like 12% of its time in memcopy, I think, which is not great. The Lexa could be faster, but I'm not entirely sure whether it would be worth it relative to the rest of the program, because there's been a lot of work recently on using SIMD in Lexas. If anyone's seen SIMD JSON, it's very, very fast.
Well, did you see the release notes for the NIM compiler? I think it was NIM, where they talked about switching different stages of the compiler to data-oriented, and they picked up a huge performance gain.
We really should be doing that. In the back end in particular, there are some little things which basically just need their data layout swapping. If you're laying out, say, an ELF file, you might lay out parts of it in memory basically flat, but a lot of the parts of, say, a section header might be only accessed fairly sparsely. You want the layout to be much more compact, which I've been meaning to do for a while, but I keep getting distracted / put off by trying to like refactor other things in the back end.
I've never used perf. Perf is Linux only, right? Or POSIX only?
Linux only. It's a front end for a system called perf event open, the perf event subsystem. So it's very, very mated to Linux. I assume there is an alternative in BSD land, but I'm not sure if there's anything as integrated as perf, but they have the same basic APIs for actually accessing the data. Vtune works on FreeBSD, as far as I'm aware.
Brian says we have PCTR on OpenBSD. Good profilers are hard to find, I guess. Are you interested at all in expanding your experience and skill set in this direction to be a valuable team member on somebody's team someday?
When you say profiler, do you mean users of profilers?
I'm sorry. Yeah, I'm talking about people.
Yes, I see. Yeah, I mean, it's definitely endearing to me, like the idea of kind of being a performance guy. I like with physics, the route into, say, like HFT work is fairly well trodden, for example. But, it depends. It's something which I would rather make it stay fun rather than turn into a chore. I'm kind of tempted by, when I finish my degree, maybe reorienting and trying to be a chip designer, but I don't know.
Elijah says performance metrics are, I think, doable with dtrace.
They might be, but I've never really used dtrace. I've used eBPF quite a lot, but it's not fantastic for actual performance profile. It's great for system performance analysis in terms of like actually making the whole computer work faster. It's a godsend, but I don't know.
Going back to the D language, have you profiled any range-heavy code?
Over the years, yes, but I don't really have any huge kind of wisdoms to impart. I mean, the thing to watch out for is range patterns. You basically need to watch out for the compiler getting stuck going, get data, work on data, get data, work on data, as opposed to it actually being able to see into, say, if you have something backed by an array, for example, you want it to be able to go into the array where it can start finding instruction level parallelism. Whereas if you end up, for example, with an allocation somewhere, that can ruin the compiler's day. But GCC and LLVM both do a fairly decent job. The issue with ranges as a performance thing will usually be around the edges rather than actually doing work on them, in my experience at least. Obviously, it depends on what your program does, but it's more of an issue with, say, copying things or having to copy things than anything hugely awful with the actual range itself.
Ali says, I remember cases where LDC would optimize range code very successfully.
It should do it almost all the time. Grid optimization, for the most part, is the norm rather than the exception now. And obviously, everyone sleeps on GCC, but because it doesn't support the current D version. But GDC is also extremely...
It's almost there.
Yeah, I know. Thank you, Ian. It's extremely good. If you let them both kind of rip on the same code, they're not identical, but if you look at modern benchmarks between GCC GCC and LLVM. They're pretty much neck and neck, apart from there are a few where LLVM is a bit ahead, and then there are a few where GCC is massively ahead because the LLVM people just haven't attacked the problem yet. Like the latest Phoronix test suite.
Steve says the advantage of ranges, they're templated, so all code is available for optimization and inlining. IO pipe is very fast because of this.
Yeah, but like LTO exists, it works, apart from some bits of GCC. LTO makes the build slower, but if you are looking for performance, it is massively helpful because you get the full brunt of the interprocedural optimizations without having to get things inside the same compilation unit.
We can call it here. And Max, you can give us your final thoughts.
Can I just say the same thing again? Profile more often and be prepared for your assumptions to be wrong in terms of what your program is actually doing. I'll reiterate one point I made in the thing is if you have something which is just like just ridiculously slow in a certain stage of the program, just break it in a debugger and you can get some samples from there, and that's actually enough all of the time. And if you profile something and you just have pointers rather than names in your stack trace, build with frame pointer emission turned off. You shouldn't need to, but unfortunately a lot of profilers don't understand dwarf properly.
All right. Thanks a lot, Max. I found that talk particularly informative because profiling is something I've never had the need to do because I don't release any performance sensitive code. I don't release any code except for my binding.